All right, everybody, just want to make this quick video to sort of go through the entire unit just like we did in class today. Um, I know we did it earlier, but in case you're studying at home, just want to give you this opportunity to have some extra little refreshers as well as some sample problems that I'll kind of sprinkle throughout here. So we're starting with energy. We have both kinetic and potential energy. Kinetic energy is the energy of movement. So whenever something is moving, it has kinetic energy. We represent that as Ke, and it is equal to 1/2 mv squared, 1/2 mass times its speed squared. Mass has to be in kilograms, and velocity or speed has to be in meters per second. And potential energy, that is sort of stored up energy. And for our purposes here, the only type of potential energy, there's many types. There's spring potential energy and electrical potential energy. But in this case, the only one we have is gravitational potential energy, and that is represented as m times g times h. The mass of an object times the acceleration due to gravity, which is just 10, times its height. That height has to be in meters, and again, the mass has to be in kilograms. Both of these are represented with the unit of the joule, capital J, and few problems on the test will just be, what's the potential energy here? What's the kinetic energy here? In that case, you would just substitute some numbers in for each one of these variables and solve for them. Most of the time, we're going to be combining these two together for total energy and working with that, which we'll see here in just a minute or two. Kinetic energy can also be sort of asked similar to how we worked with gravitational energy, and that is by asking, by what factor does it change if we double this or half that? So first thing is that whenever we increase either mass or velocity, that means that the kinetic energy will also increase. They're directly proportional to each other. So if one goes up, if mass goes up, kinetic energy goes up. If velocity goes up, kinetic energy also goes up. And whenever we double or half or triple the mass, the same thing happens to the kinetic energy. It is directly proportional to the mass. So if the mass is doubled, then the kinetic energy is doubled as well. The one that's tricky is the velocity. With velocity, there is that square on it, raised to the power of 2. So if we double the mass, then that will 2 squared, sort of that factor will occur to the kinetic energy. So if we double the velocity, then we quadruple the kinetic energy. Or if we half the velocity, the kinetic energy goes down by a factor of a fourth. So it is 4 times less than it was before. And we can sort of mathematically do it the same way we did with the gravitational unit. The only thing here is with the equation, the kinetic energy equals 1/2 mv squared. That half, when we do this, just gets left out. That 1/2 is a constant, just like g was, the big capital G, with our gravitational equation. So when you're doing these factor problems, don't multiply it by half at the end. That half sort of gets left out from the calculation. So putting those two sort of energies together, we get what's called total mechanical energy. This is the sum of kinetic and potential energy. It is both of them put together. And as long as the only force that is acting on your object is gravity, as long as there's no friction, as long as there's no engine occurring, that means that our total energy will be conserved. Gravity is a conservative force, which means that it doesn't add or take away energy from an object. It only can change from potential to kinetic or vice versa when gravity is the only force that is acting. So a couple equations that we saw today, sort of breaking this down a little bit further all the way into this sort of most basic equation down here at the bottom. Make sure you are very comfortable with that equation. Make sure it's memorized. If you don't have that one, you're pretty much toast. It's got to be there for you. So 1 half mv squared for the initial plus mgh initial equals 1 half mv squared at the end plus mgh at the end as well. We're saying that when we have our total energy at the beginning, that equals the total energy at the end. Those zeros were just from a particular example. They're not always going to be zero, but I can't really erase them from here. So let's do a little sample problem with that. And one of the most common ways we can see these sort of show up is in a roller coaster. So let me just kind of draw a nice little roller coaster. Yeah, that should be good. So let's say that this first hill is maybe 50 meters tall. It's a big roller coaster. And the second hill right here is just going to be 20 meters tall. So let's say we have a little cart here at the top, a little roller coaster sort of train coming across the top of that hill. And let's say that it is at perfectly at rest at the top of that hill. That's where it's starting off from. So because it is at rest, that means its velocity is 0 meters per second. It does not have any speed. If its velocity is 0, that means its kinetic energy at the top is also 0. So the only type of energy that this car has at the top is potential energy. So let's go ahead and calculate for that. Potential energy equals mgh. And let's just say for the sake of argument that it is a 200 kilogram. Apologize for my bad handwriting. It's a 200 kilogram cart or train. So our potential energy at the top is going to be m, that mass, that 200, times our acceleration due to gravity, that lowercase g of 10, times that height of 50 meters. There we go. And let's see, that comes out to be 100,000. A couple more zeros there. There we go. And that is joules. This kinetic energy up here was joules as well. So this is all just for that first, top of the hill moment. So our potential energy is 100,000 joules, and our kinetic energy is 0 joules. So our total energy at the beginning, or E initial, is going to be our potential energy plus our kinetic energy. So our total energy here is just that 100,000 joules as well. And we're going to say that this track is completely frictionless. It is not, there's no friction on this track. And because of that, we keep that same energy at every single point on our roller coaster. And that's going to help us do a couple calculations sort of down the line for it. So let's say I wanted to know my velocity down here at the bottom, not at any of these little hills, just at the very lowest point on our roller coaster. So at that point, my energy, and I'll call it energy final, but this is for the bottom of the cart, or the bottom of the hill, I should say. That energy final is still going to be 100,000 joules. Because there was no friction, these two numbers have to be the exact same. So I know that my total energy is equal to kinetic plus potential. At the bottom of the hill, because it doesn't have any height, our potential energy has to be 0. But our kinetic energy is still going to be 1/2 mv squared, which leaves us with just 100,000 equals 1/2 times that mass still of 200 times v squared. So now I went from having a total energy to now I'm just able to solve for my velocity. I can see how fast this cart is going. So let's see, times 2. Get my calculator out here. 100,000. Multiply both sides by 2 to get rid of that half, and then divide by 200. I got 1,000 as my v squared. And the square root of 1,000 is 31.6 meters per second as my velocity. So I went from just knowing, that's ugly. So I went from just knowing what my height and my mass was at the top of this hill at the start to being able to say, I know that it is going at this speed at the bottom of the hill. And we can take it one step further even. Let me clear out some of this writing if I can find my eraser. Let me erase some of this. It's not really going to let me do that, but that's great. Just kind of reverse some of this stuff. So here's what I still know. I still know that my total energy at the top of this hill has got to be still 100,000. So I know that my energy is going to be 100,000 at the top of that hill, but now that is going to have some potential energy and kinetic energy. Because I'm up off the ground, I've got potential energy, and because I will still be moving, I'm likely to have some kinetic energy as well. So first I'm going to deal with my potential energy. I've got 100,000 equals, potential energy is mgh, so 200 times 10 times 20 this time for my height, plus 1/2 my m, and v squared. Now I've got a different velocity. It's not that 31 from before. I'm at a different point. I've got a different velocity, just like I have a different potential energy, a different height. So a little bit of calculations here. Let's see, 20 times 10 is 200 times another 200. And we get 40,000, so I'll subtract that from both sides, and I'm left with 60,000. So that 60,000 is my kinetic energy at that point, and it's 1/2 mv squared. Multiply both sides by 2 to get rid of that half, and then divide both sides by 200. I get 400, take the square root of that, and that is 20. So at that point, I am moving at 20 meters per second as my velocity. 20 meters per second. So we started by finding our total energy at any point. Whatever point you can do that at, do it. And that energy, as long as there's no friction, there's no extra work happening, whether it's from an engine or from friction, wherever that energy started at, it has to be the same at every single point. So if a question asks you about a new point, reset it up. Now you know your total energy. That equals potential energy plus kinetic energy. Solve for those and work around to get the variables that you need. A lot of the time, we will have some other force besides gravity. Remember, with those previous problems, the question is, is gravity the only force acting? If the answer is yes, you use that previous equation. But if the answer is no, if there's some friction, if there is an engine, if there's some tension, there's something pulling your object, then that is considered a non-conservative force. It either adds or takes away energy from your object. So instead of being conservative, it is non-conservative, meaning that it does not keep the same total energy. We have a change in total energy right there. So a change in total energy is the energy final minus the energy initial. This is the exact same as the work done by a non-conservative force. So we can use those two sort of interchangeably depending on what the question's asking for. It might be more convenient to look at it from the work perspective, or it might be more convenient to look at it as a change in energy, that EF minus E initial. So work, just in general, is a force that acts over a distance. In order to have work, an object must move. If an object doesn't move at all, no work happened. If I'm, pushing on a brick wall and it doesn't move, no matter how long or how hard I push on it, I didn't do any work. I didn't actually make that object move at all. So the equation there is work equals the force being applied times the distance, or the delta x, the change in position, times the cosine of the angle. First off, that force and that delta x both have to be positive. Whenever you go into that equation, put them as positive numbers. They are magnitudes, not full-blown vectors in these situations. The cosine of the angle is going to take care of any negatives that have to be there. So even if your force is to the left or your displacement is downwards, directions we typically think of as negative, put them in as positive numbers. The trickiest part with this equation is the theta, is the angle. That angle is the angle between the direction of movement and the direction of the force. So the biggest issue with this is when we have an inclined plane. People see a problem where there's an inclined plane. They're given this angle and they say, oh well, it's whatever angle that inclined plane is. That's my angle. It gave me that angle. You have to look instead at where is the box moving and what direction is it being pushed in, and find the angle between those two directions. So if you're pushing a box up a ramp, it's moving up the ramp, you're pushing it up the ramp. That's the same direction, so it's still the cosine of 0. When you're in the opposite direction, like friction, always works as a cosine of 180. A box is moving to the right, but friction acts to the left. So friction always takes energy away from a system or away from an object. Down here we have our full-blown equation. Again, this is one that you definitely need to know for the test on Wednesday. The change in energy, which is the exact same thing as the work that's done by a non-conservative force, is 1/2 mv squared plus mgh final, the ending position, the ending information about that object, minus 1/2 mv squared plus mgh initial. So if a problem gives you information about the amount of force and the distance, I would go for that equation, that top equation, if it's asking you to find the amount of work done. But if it gives you velocities or it gives you heights instead, it might be a better idea to go ahead and go with this big equation down here. A lot of times that will work faster than trying to work all the way back through to your force. It's doable. Oftentimes, that being said, it's a lot quicker just to go this route. I know the equation looks a lot more meaty, but it is still going to be quicker for you. So if a problem gives you, heights and velocities, use this bottom equation to find your work. But if it gives you just the force and distance, go for that top one. So another sample problem I've got here, it says that we've got a ball and it has a mass of 5 kilograms and it is, it is 4 meters off the ground and it gets dropped. And it says that when the ball hits the ground, it is moving at 5 meters per second. And the question is, what's my change in total mechanical energy? Now, this problem could have asked how much work was done by air resistance. The question actually says, how much total mechanical energy did the ball lose due to air resistance? That's a change in total energy. But we could also say that it's the same thing as the work done. Those two, in this case, are the exact same thing. A change in total energy is the same thing as a work by a non-conservative force. In this case, air resistance is not a conservative force. So because we're working with non-conservative forces, I want to use that big equation from the last slide, not that first one. That first one only applies if we are working with gravity only. This time it said there was air resistance, so I have to include air resistance in my calculation. So I said that delta E is equal to my E initial, my E final minus my E initial. And I'm going to break that down a little bit further. I've got potential energy final minus kinetic energy, plus kinetic energy final, because potential energy plus kinetic energy is the same thing as total energy here. Then I've got minus the same thing, just with our initial conditions, our initial potential energy and my initial kinetic energy. So I'm gonna start with the initial conditions up here at the top. It said that the ball was dropped. If we are dropping a ball, it starts off with a velocity of 0. If I've got a 0 velocity, that means that my kinetic energy is going to be 0. It has to be. If I'm not moving, I don't have any kinetic energy. If I'm being dropped, if I'm starting from rest, both of those have a kinetic energy of 0. But we do have potential energy. This ball is off the ground. It's 4 meters off the ground, so mgh, I'm going to say 5 times 10 times my height of 4. And now I'm going to go to my final conditions. Finally, at the very bottom when it hits the ground, I do not have any potential energy. At the bottom, I am on the ground. I have 0 height. So my potential energy is 0, but this time I am going to have a kinetic energy. It's 1/2 times the mass, 5 kilograms, times my velocity squared, 5 squared. And that is still equal to my total energy, or my work done by that force. Either way, they both are the same thing. So 25 times 5 is 125 times 1/2 is 62.5. Yeah. Minus my initial. So 5 times 10 times 40, 5 times 10 times 4 is 200. So when I simplify that, I get a negative 137.5, and that is joules. This negative means that I lost energy from top to bottom. I started out with more energy than I had. That makes sense because it said the problem set up that I lost energy due to air resistance. Whenever we have something sort of pulling back on our object, we are losing energy. So the fact that this negative here is present makes sense. And we have it as 137.5 joules as our answer there. So either way, if this asks for a change in total energy or a change in, not a change in work, just how much work was done by air resistance, we approach the problem the same way. These two things are equal when we have a work done by a non-conservative force. So it's one way to do two different problems. They look different, but in reality, they are the exact same. Just a reminder, units for all of these are joules. Energy, kinetic energy, potential energy, and work are all in joules. It makes sense. Kinetic energy is just, not kinetic. Total energy is just kinetic energy plus potential energy. If you have 5 apples plus 10 apples, you have 15 apples at the end. It makes sense that your unit is going to stay the same when you're just adding those numbers together. Or if you add 5 meters plus 7 meters, it's still just 12 meters. The same is true with work. We said that a work was a change in total energy, so that is total energy minus total energy, or joules minus joules. It's 10 meters minus 3 meters is 7 meters. The unit stays the same. It is joules for each and every one of these. The only sort of quantity that we have a different unit with is power. And power is when we do work or we have a change in energy over time. If we continually do something, if we continually use up energy, power is also considered to be the rate at which energy is used or gained. So power is measured in watts. Our unit is watts. That's the same thing as a joule per second. So when you think about a light bulb that says it's a 60-watt light bulb, that uses 60 joules of energy per second. Because of that, when we use this equation, our time must be in seconds. So you might take a look and think about remembering how to convert, maybe minutes into seconds, or hours all the way into seconds. Make sure you are working in seconds when you do those calculations. The kilowatt hour, just briefly, just a little side note, is actually a unit of energy, not of power, even though it has the watt in there. The hour is a time, so those seconds actually cancel out, and 1 kilowatt hour is just 3,600,000 joules. So let's just do a quick example here with power, and then we will call it good. Oh, let's see. Let's say that we had a light bulb. Let me see if I can draw a little light bulb here. That's a terrible drawing, but it's okay, That's a light bulb. I've even labeled it. That means it has to be true. So we've got a light bulb, and it is a 60-watt light bulb. Pretty common household light bulb. And let's say that I left this light bulb on. I actually left a light bulb on in my house over the Thanksgiving break. I actually left it on for 48 hours. I left it on for 2 days. I completely left town with it on, which cost me, but hopefully it won't be too much. So let's say that I left this on for a total of 48 hours. My question is, how many joules of energy did I use up? How much energy got used? What was my change in total energy here? So I know I've got a 60-watt light bulb, and if I say that power is a change in energy over time, my power is 60. I'm looking for my change in energy, and I need a time. So I've got 48 hours, but remember that time has to be in seconds. So I'm going to convert hours into minutes. I've got 48 hours. Let me back up a little bit. And in 1 hour, I've got 60 minutes. And in 1 minute, I've got 60 seconds. So each one of these cancels. The hours cancel with the hours. The minutes cancel with the minutes. And I'm left with just a unit of seconds. Let me see how many seconds 48 hours would have been. 48 times 60 times 60. So I got 172,800. Let me throw that in there. 172,800. So that is my time. That is in seconds here. So if I multiply 60 by that number, I should get my joules out. And it is a change of energy. I used up 10,368,000 joules of energy. That is a whole lot. Not entirely happy about that. It's going to cost me probably a couple bucks just because of that on my electrical bill this month. But hopefully I can afford it. I am a teacher after all. We make the big bucks. That was a joke. But anyways, that pretty much sums up the entire unit in class. Hopefully you got all the help you needed as far as sort of more of the examples. We're going to do that here on Tuesday, or if this is just being watched for the first time by some of you on Tuesday, we did those today. So hopefully that sort of satisfied your appetite for some physics problems, and hopefully you're feeling ready for the test. As always, thank you all for watching. Hope this is a helpful and enjoyable experience for you. And hope good luck on the test, everybody.